So today I'm going to talk about one of the problems. Mathematically, it's one problem, but its applications is from homogenization and also micro-magnetism. And this work has been in collaboration with Asir Abdul, who was my postdoc mentor at École Polytechnique Fédérale de Lausanne. And sadly, he passed away in 2021. And Eduardo was the PhD student at EPFL that I was mentoring. And Philippe Martalla here is my current PhD student at Uppsala University. And Victor Martinez is my collaborator from Mexico at the moment. So I would like to start with the problem of homogenization, and then sort of we will get an understanding of why we deal with the infinite domain problems here. So assume that we have an elliptic PD, and here we assume that a epsilon is a rapidly varying function of wavelength of size epsilon, and epsilon is assumed to be much less than the domain size, and we assume that the domain size is of order 1 for now. And just for simplicity, f and g are smooth functions for the moment. And so if we look at a epsilon here, a epsilon is typically modeling the material behavior, and this is seen in many applications in engineering sciences. And for example, if you take the portion of an airplane, the wing here, then macroscopically the material is homogeneous, as we see in the right picture here. But if you zoom in microscopically, then we can observe some heterogeneities in the micro scale. And this is due to the fact that typically we use composite materials for engineering these type of materials. Now, okay, so slightly going into numerics now. So suppose that we have a coefficient a epsilon, and here the wavelength of the epsilon of the coefficient is denoted by epsilon. And if you would like to solve this with standard numerical methods such as finite element or finite differences, then the cost scales as epsilon to the power minus t. And as epsilon gets smaller and smaller, this is tremendously expensive to solve. So the idea behind homogenization is essentially replace this a epsilon here with another coefficient, a0 for now. And a0 is much smoothly varying and is totally independent of the small parameter epsilon. And then we solve the resulting system at a cost independent of the epsilon. So this is essentially the main idea here. So the problem statement is then given a epsilon, we want to approximate a0, the coefficient, or u0 in an accurate and efficient way. So here I would like to give some examples of heterogeneous media, and some of them is sort of will be valid for the theoretical cases that we study, and some of them they are essentially relevant for numerics that we do. So here you see two periodic materials here. The first one is a discontinuous coefficient, and the second one is a smooth coefficient, but both varying at a very small scale. And then there are also examples of non-periodic media. The first picture that you see in the top left, that's a quasi-periodic coefficient. And here is just a cut of the function is plotted. And then if you look at the picture down here, then we see a checkerboard type random material. And the analysis will also be valid for this type of materials. Okay, but we also will do the numerics for heterogeneous of this kind, for which the theory doesn't apply. Not part of the theory doesn't apply. So we will see it in a nutshell. So there are various multi-scale methods which has been designed over the last 2 decades to tackle such problems. And myself, I have been gaining experience in heterogeneous multi-scale method, essentially these two. And this was since both methods, they were maybe designed in very, very close time. So both close to 2003. HMM and equation-free approaches, but there are also other types of methods which are cited here. Essentially, there is the main difference between these two is that the set of methods that are cited here, they are working for problems where we have continuum of scales. So essentially, we don't have a scale separation for these problems. And then for the last two methods or methodologies, they are typically very useful when we have scale separation. So when epsilon is much less than the size of a domain. So that's what I mean by scale separation. So, but the methods that we discuss here, they are applicable also so to both setting here. So one can use in both settings. For example, one can use in these two, and one can also use in MSFM or no, I'm not sure about the rest, but yeah, I'm sure that one can also use in MSFM. Okay. So now if we go to the mathematics of it a bit, suppose that we are given a periodic material. So a epsilon is given as a x over epsilon, where a is a periodic function. So, and for simplicity, we say like a is one periodic in every direction. Then the homogeneous coefficient is given by, well, this quantity, and mk here is the is an average operator here. And if you look at this term, here we have a naive average of a, the original coefficient, and then here we have an extra term which appears. And this is due to the high frequency variations in the problem. So, and here the function chi solves the following elliptic PD with the periodic boundary conditions. And these will be called the correctors for now. Okay. So now what we say here is that if the material was periodic, then we had to solve only a periodic problem here, okay, over the unit cell. But now in engineering, it's very typical that maybe the material is periodic or very close to be periodic, but we don't know the period. We don't know what the period is. Or the material is, let's say, random. And so now if we assume that the material is stationary ergodic, if you have a stationary ergodic randomness, then A0, the homogeneous coefficient, will be given as the limit of A0R, where A0R is sort of an average. It's very similar to what we had before, but here we have something called KR. Okay, so KR is now, I'm going to explain here. So KR is a domain of size R to the power D. And now the correctors will solve a problem, well, very similar to the first periodic problem, but now the problem is posed over the entire KR. And as R tends to infinity, we obtain the homogeneous coefficient. So essentially, instead of having KR, we can have what we target is to solve an infinite domain problem here. Well, in general, if you don't know the period, or if you have, let's say, stationary ergodic material. Okay, so this is where the problem of infinite domain elliptic PDEs come in homogenization theory. Okay, so once again, I want to emphasize that, okay, so maybe the material is periodic, but we assume that we do not know the period. Because if we had known the period, then we could easily solve this problem instead. and we are done. So there's nothing interesting there. Okay. So now about the convergence rate. So if we just assume a periodic material, and if we look at the difference between the exact homogenized coefficient minus the A0R that we computed here for a fixed R, then the error scales as 1 over R. And this is very problematic because, yeah, suppose, well, in applications or in computations, we cannot afford very large values for R. And this decay of the error is just first order in R, in 1 over R. And so therefore, we need a very large values for R to obtain small errors. Okay? And this is computationally very infeasible. And similar results also exist in the stationary ergodic setting, where now the first order rate is replaced by some order between 0 and 1. Okay, so now again, I want to once again emphasize that we really need higher order convergence rates. And okay, so and that is due to the fact that in practice, we can just maybe tolerate moderate values of R. For example, R is equal to 10. But then if R is small, 1 over R becomes large, and this leads to low accuracy. So our goal is then to design potentially some corrector problems which are elliptic. And essentially what we like is that we have high convergence rates higher than 1. So here for some Q, which is larger than 1. And we don't want to spend too much computational time in comparison to solving one elliptic PD. Okay. Okay, so what has been done in literature? So people have tried imposing different boundary conditions, such as periodic, Dirichlet, and Neumann boundary conditions. So here in this work in 2007, they found out that periodic boundary conditions lead to a smaller prefactor, but it doesn't improve the rate. So the convergence rate becomes still first order if one just simply changes the boundary conditions. Okay. And then there is also idea of oversampling. And oversampling means that we solve the elliptic PDE, well, that corrector problem, in a larger domain. But when we take the average, we average over a smaller domain. Okay, so that's the idea of oversampling, and that is still of order 1. And then there is a very promising approach of Blanca and Lebris from 2010, where we really get high order convergence rates. So let's say in one dimension, it gives indeed much higher order convergence rates, but in any dimension, the convergence rate is 2 here in the third approach. And then in 2011, there is a result due to Antoine Gloria, and we will call that zero order regularization. And we are going to explain it here because that's one of the methods which gives fourth order. And there was an approach based on changing the corrector problem from elliptic to hyperbolic. And that's due to myself and Olof Rambori in 2016, where we could get arbitrary the high convergence rates here without spending too much computational time. And then I have also worked on different methods for this problem because I was not really satisfied with the wave approach that we were designing. Then in 2019, there we came up with two different approaches. And then here in paper number 2, here we do the analysis for the, so let's say, okay, so in 2019, we designed 2 different methods. One uses a parabolic corrector, and the second one uses an elliptic corrector problem. And this paper 2, that includes the analysis for the parabolic model, and paper 3 includes the analysis for the elliptic model. And there is also a result on stationary ergodic problems where we extended the analysis of the elliptic model for random materials. Okay. So there are other promising approaches also in the literature, but still well, these are more recent, but they still lack high order convergence rates in any dimension. Okay. So now I would like to, this is the plan now. I will go through these 2 approaches, zero order regulation and the wave approach. And then I will just in one slide mention our parabolic approach. And finally, this is where I want to finalize my talk. So that's about the elliptic models for obtaining high order convergence rates. And so, by the way, so in the new approaches also, we have arbitrarily high convergence rates, arbitrarily large convergence rates for this problem. So all these methods, they give arbitrarily large values for Q. Okay. So now to, this is sort of preliminaries here. This is one idea that we will be using quite a lot. So that's related to averaging kernels. So suppose that we have a function which is symmetric, well, even function, and we have certain smoothness properties here, and it's compactly supported, let's say, in -1/2 and 1/2 closed interval. And we say that mu has p vanishing moments if the following condition is satisfied. Okay, so now just to illustrate the idea, suppose that now instead of suppose that we are interested in the average of a function which is one periodic. Okay, if we now define this weighted average, so I denote that by calligraphic MKL mu, then, well, this guy will be very close to the exact average and plus some errors here. And the error here scales as L to the power -q-2 if you use a qth order, and Q here is the smoothness of the filter here. Okay. And here, if we have, let's say, a naive average, so right now, if mu is just a constant, then we just expect the first order convergence here, okay? And this illustrates. So in the left figure, we just see the blue one is the function that we are averaging. And the red one here is the mu that we are using. So in this case, it's a constant function, which amounts to q is equal to -1. Then the rate here, as L increases, becomes order 1, the rate. Okay. So now if I just slightly increase the value of q, so let's say if this red one is the new weight function that we are using, then we expect second order convergence here for the to the average. And similarly, if you use a high order q, then we get yeah, for q is equal to 2, we get fourth order, etc. Okay. Okay, so now this averaging kernels is common to most of the algorithms that will be presented here. So that's why I wanted to illustrate this in one slide. So now, as we promised, we are going to look at the zero order regularization. So the idea is as follows. In the original cell or corrector problem, we only had these two terms. Okay? In the original PD coming from corrector problem coming from the homogenization theory, which was periodic. And for now, we can still assume that A is periodic, but that we don't know the period. Okay? And what Antoine Gloria does is just to add one regularization term, which we call it zero order regularization term due to the fact that there is no essentially a differential operator acting on U here. And T is just a parameter here. And KR, so here, I hope everybody can see. So KR is a domain which is chosen to be sufficiently large. And the averaging here, it contains, again, two terms, but it's taken place over a smaller region, which we denote as KL. Okay. So, and this is sort of the idea of oversampling. So if we apply this strategy, then the error estimate that we get is in the periodic setting upon choosing optimal values of T and R is as follows. So we get R to the power minus 4. We get almost fourth of the convergence in 1 over R. And this is essentially due to the fact that if we didn't have this term, the first term, then the Green's function decays very slowly for just this elliptic operator. But as soon as we add this zero order regularization term here, then the Green's function decays exponentially. And therefore, the error that we are making on the boundary, so here, this is just an artificial boundary condition that we are putting as, suppose that it's Dirichlet, homogeneous Dirichlet. Then this boundary condition will, the effect of this will decay exponentially in the interior domain. Okay, so that's the idea. Basically, by adding this term, we are changing the Green's function of the problem. Okay, and then we are able to obtain up to fourth order convergence rates in periodic material. And okay, so this estimate is under optimal conditions on T and R. But if we use any fixed T and L, this would be the full estimate. Okay. Here I would like to emphasize in his paper from 2011. This rate, of course, from analysis point of view, is asymptotic, but also in numerics is observed for very large values of R. So, and this is still computationally, well, a bit expensive. Computation very expensive if the size of a domain is large. Okay. So this motivates why we need better approaches. Okay, now the second idea is based on the wave equation. And here, instead of having an elliptic corrector problem, now we assume that we have a wave equation. Now the problem is that U depends both on time and space. And again, if you just look at this term, this is what we had before for the corrector problem. But now, of course, we have a wave equation. And the solution depends on time and space. And now if you want to compute the A0, we average over time and space, both time and space. And these are weighted averages with our filters with certain smoothness. And so one idea here, okay, so in the beginning, it might sound a bit awkward, so because we are changing the local problem, the corrector problem, from being elliptic to hyperbolic. But essentially the main idea is that if we look at this time average of this wave equation, the solution to the wave equation itself. So if you look at this integral, denoted in red, then the time average of the solution actually stays very close to the solution of the original elliptic problem over RD. So essentially, we don't see any boundary effect if you only look at the time average of the solution of the wave equation. Okay, and this is first. I would like to come to this part here, and this is due to the finite speed of propagation of waves. So essentially, this means like, okay, so the error that we are making on the boundary. So here we have artificial boundary condition, which is 0. It will not have sufficient time to go into the interior of the domain if the domain itself is chosen to be sufficiently large. And this is due to the finite speed of propagation of waves. And here we are able to prove that if A is one periodic in every direction, and if the domain is sufficiently large, okay, and so that the errors on the boundary do not propagate into the interior, then we can prove that this does not add any computational complexity. And typically we have mu with q even to infinity, okay, at hand. So it's not a problem at all. Okay, so this is the wave approach, but what about the challenges? So here what we see is that first of all, the problem is time dependent. So if you want to numerically solve this problem, we have an additional dimension to handle, although the cost does not increase with respect to the oscillations that we have in the in the coefficient A. And the second thing is that the domain size here R needs to be chosen sufficiently large. So essentially, if we have a coefficient which has high contrast, then the domain size will be very large. And okay, so that's one of the challenges. So there are two essentially challenges: time dependency and the fact that we may need to choose very large domains, okay, to obtain such errors. And then there comes in 2021 another approach. This is now based on parabolic cell problems. And now instead of a wave approach, we solve a parabolic PD. And we compute the homogeneous coefficient using a different formula, but still it contains integrals in time and space. And now the convergence rate heavily depends on how we choose the parameter capital T. So capital T is here the final time of the simulation. So this is T here. If T is equal to infinity, essentially we are looking at the steady state of this problem, and we get no improvement in the convergence rate. So still we have 1 over R. But if T is chosen sufficiently small, then we are able to, well, I'm ignoring these errors because they are much smaller than the first term here. Then we get R to the power minus Q for arbitrary large Q, okay? Essentially what we have is an exponentially decaying errors for the approximation of homogeneous coefficients. And one thing that I want to emphasize here is, well, once again, is the fact that T needs to be chosen sufficiently small. And this is due to the fact that the Green's function for the parabolic PDEs, well, we have a Gaussian decay in space. Okay, so we cannot allow any large time, because then the errors on the boundary will have a time to influence the interior solution. So this is essentially the physical motivation behind it. But okay, so overall we have this estimate if we choose T optimum. And here I just want to put assumptions. Well, normally what we would like in applications is that we just need the coefficient A to be bounded from... Sorry?
Excuse me, please. Could you please recall what is L here?
L, okay, just a second. So L represents the size of the interior domain where we take the average.
I see. Thank you.
Okay, and R is the size of the domain where we solve the problem. Okay, so here I would like to just give the assumptions also. Well, although it's a bit technical. Normally in applications, what we face is that A, so this is to say that A is bounded from below by alpha and from above by beta. Okay, so the first assumption, and this is needed for well-positiveness of the problem. So there is nothing strange in that. But then we also need the additional, for this proof, for this theory to work, we also need the an additional condition where A needs to be in W1 infinity over KR. Okay, so we also need that assumption. And assumption 3 for now, we can just ignore it, because, well, I think I will not be able to explain what V is at the moment, but okay. But it's, well, it's just slightly stringent than what we already have in PD theory, just with it, well. Okay, so now finally we come to the elliptic approach that I wanted to discuss. So far we have gone through the glorious zero-order regularization, which gave fourth-order homogeneous rate. We have gone through the hyperbolic second-order hyperbolic corrector problems that gave qth-order homogeneous rate for arbitrary large values of q. And similarly, parabolic corrector problems that also was giving exponential decay with respect to the domain size. And now, this is a long-standing idea that I always had in my mind, to have a local problem or corrector problem which is time independent. So it should be elliptic, but also it gives any desired homogeneous rate. So this is sort of an idea that or motivation that I had behind all my work in this direction. And so the idea behind solving elliptic corrector problems is as follows. So now, if you look at this term here, where G is the divergence of A, this is the standard local problem that we had. Okay? This is the standard corrector problem. And now what we do is just that we essentially add one extra term, which contains the exponential power of an operator, A. And A here is just the elliptic operator that we have equipped with the homogeneous Dirichlet boundary conditions here. Okay. So now, instead of the original local problem, we solve this the corrector problem with an exponential regularization, and we compute again the A0 using over So we average over, but we solve the R is larger than L. Then we are able to prove, again, exponentially decaying bounds for the approximation of the homogeneous coefficient. And here, again, okay, so this is based on optimally choosing the values of L and R, so L and T. And the idea behind this is also very similar to the parabolic approach, but the formulas are much different there. So essentially, there are two differences. First of all, our problem now is time independent. So we have a parameter capital T, but this just enters as a parameter in the problem. Okay, so there is no time dependency here. And well, the second one is not a difference, but it's more like a similarity, that the scaling of the optimized parameters is very similar to the parabolic approach mentioned in the previous slide. And the bound that we obtained is essentially one term where we have r to the power minus q, and then we have an exponentially decaying bound in terms of r. So if we so this implies that we don't need to choose very large values of r. Okay, so and essentially the fact that we can play with q without spending too much computational time, well, this method becomes extremely, in terms of computations, extremely efficient. Okay, so what is the motivation behind this? So I would like to motivate why we have this term here. Okay. Now, the original PD that we had, it was only this term posed over RD, over the entire domain. This was the reference. And now we are just simply replacing the RD with KR at the expense of adding one extra term. Okay, so let's go to the motivation now. Suppose that we are given the following parabolic PDE. Now I just define chi to be the integral from 0 to t of the solution u. Then just applying this integral operator here, what we see is that yeah, so if we apply the elliptic operator to chi, then yeah, we just use this formula to write it in this way. Then we can use the PD and figured out that this term here, the elliptic operator acting on chi, is equal to ui0 minus uit. But ui0 was given as divergence of A. So this is divergence of A. And then uit is given as exponential minus TAG. Okay. So now here is easy to see that when t goes to infinity, then we recover the original local problem. Okay, so this is taking t equal to infinity doesn't help that much. Okay, so it gives again first order convergence rate. So it's again really important that we have right scaling for t in terms of the domain size R. Otherwise, we do not get any high convergence rate. Okay. This is sort of the motivation. Well, it doesn't motivate why we get high order convergence rate, but at least motivates that as t goes to infinity, then we are recovering the original local problem, but posed over the domain KR. Okay, so now I would like to address the numerical approximation of this problem. So I should maybe come here. So of this problem, I mean. So if we discretize this, of course, we will get some linear system here. But the most important is approximation of this exponential power of the operator. Okay. And this is exactly what we have here. So we have some metrics coming from a finite difference or finite element approximation. And then here we have the right-hand side G, and we have this exponential power of metrics. Okay, so how to compute this now? So for this, we do some, we resort to some algorithms based on Arnoldi. What we do is the following. So we say, well, instead of working with A, which can be, which has size n by n. So here I should have denoted that. So A here, the matrix A has size capital N by capital N, okay? And it is assumed that K is much less than N here. So, and the matrix H is K by K. Okay, so now instead of working with A, we work on H, which has a much smaller size. So because of K. And then, okay, so we have also some matrices here denoted by Q and Q star. And this is the important result for computation of this matrix exponential, and that's due to Hochbrook and Lübich from 97. So now this essentially means that instead of computing the matrix exponential of a very large matrix, we can only compute the matrix exponential of a very small matrix here, exponential minus h. And this will then, the error will decay, as you see, exponentially with respect to the size of h, which is k. Here we have the same k, okay? And the overall computational cost of solving this problem is dominated by the Arnoldi algorithm. So solving this linear system is much cheaper than solving the corrector, the exponential power of the operator here. And the cost of solving this for a problem size of n by n is n times k squared. Okay. So if k is small, and in my numerical simulations, typically I only use 15 to 20. Even the problem size is 300 by 300 or 500 by 500. So I typically use very small values of k. So this doesn't go beyond linear scaling. And this is the optimal value. If we want to optimize all of the errors in the computations, then we have to take n to the power 1 over d. Okay, so it's, well, you have almost linear convergence rate at the end, computation cost at the end. And here comes some numerical examples. So if you have a periodic material, okay, so here we have the standard elliptic, the red one. By standard elliptic, I mean that we just take the local elliptic problem and we just truncate the domain from infinite domain to finite domain. Okay, so that's the standard elliptic. And that gives 1 over r as predicted by the theory already. But now, if we apply the elliptic approach that we proposed for different values of q, then you see that as we increase the value of q, we get improved convergence rates. So here on the x-axis we have the value of r, and on the y-axis we have the error, right, for the homogeneous coefficient, for computing the homogeneous coefficient. So Q2 is on blue, and Q5 gives a slightly better convergence rate, and these are all predicted by the theory. And essentially, the theory here was valid for the periodic media. And now I wanted to see also what happens when we have a periodic media, but with a high contrast. Okay, so if you have questions related to this, we can go back to that. So I will also go through the other slides first. And here we also see that, well, unfortunately, I didn't have too much computational resources to continue this, but asymptotically, we should be able to see that we have better convergence rate for higher values of Q here. Okay. And by high contrast here, I mean that the coefficient, well, you see the value of the coefficient. So this is the coefficient that we have. This is a epsilon. And is the ratio between the maximum value of A and the minimum value of A scales like 100 here. Okay, so that's what I mean by high contrast. Okay, so another case where we study numerically is when we have discontinuous media. And this is also a case where the theory doesn't apply. But still, we are able to observe improved convergence rates upon choosing higher values of Q. Okay. So as remember that in the theory, we assume some regularity for A. We assume that it's in W1 infinity. And this is now another case where we do not even have periodicity. So as you see, due to this term that we see here, this is not a periodic function, but a quasi-periodic function. And this is how the cuts are looking like. And in this case, we are able to also observe very high convergence rates as we increase the value of R. This is still a case where the theory doesn't apply, but I just wanted to test the method itself for the cases beyond periodicity. And finally, we have a totally heterogeneous material, but now I look only at the effect of the boundaries. So if I just increase the value of R, so okay, so I need to explain this a bit. The reference here is A0 is computed by choosing a domain of size R max. Okay, and then I compute A0 for smaller values of R, and I look at the difference between them. But this is all the time fixed. The R max term is already fixed. So this is the boundary error that we have for this modeling. And here we can observe as R goes to infinity, we obtain an exponential decay in R. And this is yet another example. And here my aim was to compare how the proposed elliptic approach compares to the standard elliptic, and also to the zero-order regularization approach of Antoine Gloria. Okay, so in the first plot, we see how the errors are decaying. The blue one is the method that we proposed. And as you see, as R tends to, as R gets larger and larger, we have a much smaller, well, much improved decay rates in comparison both to the zero-order regularization approach of Gloria and the standard elliptic. So here, actually, it's worth noting that, as we mentioned before, the zero-order regularization approach needs to be actually fourth order. But here, since we are not in the asymptotic regime, we observe only 1/2 convergence rate. And this is due to the fact that those asymptotic rates are seen for very large values of R, example 50, that R is equal to 50, where we also mentioned in the first slides. And here I wanted to compare the computational cost to achieve a certain tolerance. And here in the x-axis, we have the error that we obtained, the exact error that we obtain in the computer. And on the y-axis, we have the computational time. And as we see asymptotically, the modified elliptic approach that we propose, it has much better, well, slowly increasing a rate for the computational cost in terms of the error that we are interested. And the red one is the standard elliptic. Well, asymptotically, that's not very good. And the second one is the zero-order regularization of Gloria. And the blue one appears to be behaving much better asymptotic. Okay, so I would like to just maybe skip these slides here, because yeah, I want to just in 3 slides also mention a new problem that recently we had some results on this, and that is related to the Landau-Lifshitz-Gilbert equations of micro-magnetism. And this is a nonlinear partial differential equation where the right-hand side is now contains a term called H, the effective field. And this has many contributions, but so I'm skipping all of these, but I'm just interested in this, the so-called demagnetization field, which is the most time-consuming part of these computations, because this needs to be evaluated for every time step. Okay, so the demagnetization field is given by the gradient of a potential, and this potential now solves an infinite domain problem. But the right-hand side is equal to divergence of the magnetization over a domain where we have the magnetic body, and in the rest of the domain over RD, we see that this is equal to 0. Okay. And typically, people they represent the solution U here using the following integral representation, where G is the Green's function over RD. And if we just naively implement this, we see that the computational cost to compute the solution over the magnetic body scales as n to the power 2d here, assuming that we have n degrees of freedom in every dimension. Okay, and so there are methods to improve this computational cost, or to decrease this computational cost. And I would like to just quickly mention the method of Garcia, Caveira, and Roma from 2006. And that is based on splitting the solution U into 2 parts, V and W, in the following form. So here, essentially, we have 2 PDEs. The first one is just a Dirichlet problem over a bounded domain, omega. And the second one, that's an infinite domain problem, but the solution can be represented by an integral representation here. Here, G means this, okay? And so now if you look at the second, so we don't have any problem with the first problem, because that's just an elliptic PDE to solve. And the second one here, the strategy here is just to evaluate the function values V only for the boundary values, for X only on the boundary, and then solve the Laplace equation here inside the domain. So that's the strategy. And then in that way, they improve the cost to n to the power 2d minus 2. And here, this is a recent result that we have now with Victor Martinez from Mexico. So we split the solution in a different way. So we have one term, VTR, and VTR now you can see the similarity to what we had from homogenization theory. It solves the following elliptic PD with exponential regularization term over a domain KR, which is slightly larger than omega, but not that large because of the exponential decay of the error. And also we have additional term G, and G solves again one elliptic PD over omega, where the boundary values are only computed by the boundary integral. Okay, and this actually gives a cost very similar to Caveira Roma from 2016. So both algorithms, they have the same computational cost, but the advantage in this method is that we propose is that now the equations for V and for G, they are totally uncoupled from each other, and this is much suitable for parallel computing. So if you compare this to here, we see that value here is used in the second equation. So, well, this algorithm is not good for parallelization. We cannot parallelize it, right? But here, now, these two equations, they are totally uncoupled. And so that would be the advantage. So we have some theoretical results on different theoretical settings than periodicity here also, but I will not have time to mention those. Yeah, thank you for listening.